Hello, my name is Thais Arslanbekov, and this is my lab report for Lab 3, Magnetic Field of a Bar Magnet. For the purposes of this lab, a bar magnet can be considered a magnetic dipole with a north and south pole. Therefore, the formula for the on-axis magnetic field of a dipole must be used to calculate the magnetic field produced by the bar magnet. Similar to electric fields, magnetic fields can be added using the principle of superposition without affecting one another. A computational model will be utilized to compare numerical analysis results to those produced by written code. Magnetic fields will be visualized using the aforementioned code in order to compare different models. The first two formulas quantify the magnitude of a magnetic field due to a magnetic dipole. The first formula defines the dependence of the magnitude of a magnetic field produced by a bar magnet as proportional to some constant times some power of the distance. These will be relevant in order to calculate mu, the magnetic dipole of the bar magnet. The last equation linearizes the data points in order to find values for the first formula and then sets it equal to find values of mu from the second formula. The third formula will be utilized in the computational model in order to compare with the numerical results. The first setup is used to calculate bx's for certain distances r and then generate linearized plot to find the values for k and n. The second setup is used to find the distance where the magnetic field generated at that distance is equal to 100 microteslas. Then, the net magnetic field at the location marked x was calculated and then will be compared to that found by the computational model. Here's a look at the experimental data, which shows raw calculated values as well as a linearized plot of ln bx versus ln r. The bottom right calculates the net magnetic field of a point 45 degrees off axis. This data will be used to perform subsequent calculations. These equations are set to be equal to each other in order to find an equation to find mu, the magnetic dipole moment of the bar magnet. Then, the linearized ln bx versus ln r graph will be analyzed to produce the values for n, r, and k, and plugged into the aforementioned formula to calculate mu. My calculated value for mu is 3.16 newtons meters per Tesla. Only the first and fourth assumptions are valid. I noticed that whenever the magnetometer was placed very far away from the magnet, Bx was incredibly close to zero. As I brought the magnetometer closer and closer to the bar magnet, Bx increased as expected. First, I defined a function dipole B as a function of mu, the magnetic dipole moment of the bar magnet, and r, which calculates the magnetic dipole at a specified observation location. Here's the formula I employed for reference. The magnetic field will be visualized at these locations. The first 2 points lie on the axis of the dipole, whereas the remaining 4 are perpendicular to the dipole axis. Then, I drew arrows to visualize the magnetic fields produced by all 6 of the aforementioned axes, and then calculate their magnitude due to the defined dipole B function. Finally, I performed the same structure but for an axis 45 degrees away from the observation axis. I similarly drew an arrow to symbolize it, and then calculated its magnitude from the dipole B function. Here's a visualization of the code results. The 2 orange arrows are the on-axis magnetic fields, and notice that their magnitude is twice that of the perpendicular axis magnetic fields, which coincides with the given formula. The 4 cyan arrows represent the perpendicular axis magnetic fields, and the magenta arrows the magnetic field produced at 45 degrees off the observation axis. The scale is 10 to the negative third because this is proportional to the magnitude of the magnetic fields produced on each of the aforementioned axes. The most interesting result is the value for the magnitude of magnetic field 45 degrees off axis, which is outputted to be approximately 2.77 times 10 to the negative 5 teslas. Now we compare these values calculated from the computational model to the numerical analysis of the data. These two values are not approximately equal. It is evident that in this finicky experiment, there are plenty of opportunities for human error and other magnetic field interference, so I'm thankful that these two values are at least in the same order of magnitude, which means that the results are at least slightly accurate. Therefore, the experimental method could stand some improvements in order to be more accurate, so that the result could be closer to the computational model. Here are some of the what-if questions. All of the measurements for Bx would be skewed by the same amount due to interference from the Earth's magnetic field. And due to superposition, this would also have skewed the measurement for the off-axis magnetic field, which is calculated at the very end. I would expect that all of the Bx's would be multiplied by some positive scalar constant if 2 magnets were stuck to one end, because this is basically equivalent to replacing the 2 magnets with the stronger magnet and then repeating the experimental setup. The relationship found in the results would stay the same, but the numerical values would be different, since the orientations and relative positions of the magnet do not change, but only the magnetic dipole mu would change. Thank you so much, and have a great rest of your day.